Hi class, this is Sir Alex Basco and welcome to our lesson in General Chemistry 1. Today we are going to discuss ionic bonds. This is lesson 12 and we are going to discuss what ionic bonds are, how they are formed, how to write their formulas, as well as how to write their structure. You will notice as we go along with our discussion on the structure, you will find a very familiar way of writing them called the Lewis dot structure, which we have learned previously. So let's begin our discussion by first understanding octet rule. Octet rule is very important to understand because it helps us and guides us in understanding the formulation or the forming of ionic bonds. Let's discuss octet rule by first understanding why noble gases are what they are. Why are they stable? Well, noble gases, or the elements that you will find on group column 8A, they are stable is because their outermost shell or their valence shell are filled. Remember, each valence shell, except for the first shell, always want to have 8 electrons. And on the first shell, it wants to have 2 electrons. When this valence shell are satisfied or filled up to their number of electrons, then they become stable, such as these following noble gases that we have. Helium has 2 electrons in its outermost shell, which is the first shell, so it can only have 2 and it satisfies that number, making it very stable. And if we look at neon, argon, and krypton, you would notice a trend of having 8 electrons at their outermost shell. You can say that these 8 electrons are the outermost shell because if you look at their main energy level, for example, neon has main energy level number 2. Remember, main energy level is just telling you the distance of these electrons from the nucleus. The bigger the number, the further the distance. But having these 2 electrons and the 6 electrons fall at the main energy level number 2, it means that they all at the same distance from the nucleus of your neon. And even though they are at different orbitals, s orbital and p orbital, since they fall at the same distance, you can think of them as having the same or falling on the same shell, which is the valence shell. And since there's 8 of them in that shell, it satisfies the octet rule, which means it wants to have 8 electrons on their valence shell so they become stable. The same thing for argon, where you have your 3s2 and 3p6. s2 and p6 are found on third main energy level, both distance from the nucleus of your argon, which means this 6 or this S2 and P6 are basically at the same distance from the nucleus of your argon. So hence you can think of it as finding them at the very same shell, which is their outermost shell, and at their outermost shell you will find 8 electrons there. And the same principle for krypton. And if you go look on all your noble gases, you will find this trend of having S2 and P6 at the end of their electronic configuration. Except again for helium, because helium only has 1 shell, which satisfies that of having only 2 electrons. And this is the octet rule. Having 8 electrons on your valence shell, especially the valence shell, which is your outermost shell. So every time you hear me say valence shell, I'm talking about the outermost shell. It satisfies the octet rules, which makes the electron very stable. So why is this important in forming ionic bonds? Well, in forming ionic bonds, it's basically a way for the atoms of the ions or the cations and the anions to satisfy their octet rules in order for them to be stable. And that is because the atoms, when they form ions, they either gain or lose electron, and they want to gain or lose electron in order for them to satisfy the octet rule, or having 8 electrons in their valence shell. So let's look at some example on how do we identify which elements gains and which elements lose electron in order to satisfy the octet rules. So let's look at our sample problem 12.1. One of the most common, if not the most common ionic bonds or ionic compounds that we have is NaCl. NaCl, which is the compound for um, table salt, is a combination of sodium cation and chlorine or chloride, chlorine anion or chloride. So let's look at the electron configuration of a sodium cation and a chlorine anion. What we're going to do first is let's first write the electronic configuration of a normal or neutrally charged sodium and a neutrally charged chlorine. On a neutrally charged sodium, you will find that the electronic configuration is 1s2, 2s2, 2p6, and 3s1 because sodium has actually 11 electrons, while chlorine would have an electronic configuration of 1s2, 2s2, 2p6, 3s2, and 3p5, which tells us that chlorine has 17 electrons. This is the electronic configuration of a neutrally charged atom of sodium and chlorine. But what happens to the electronic configuration of sodium cation or a positively charged sodium and a negatively charged chlorine? First, let's understand which one loses electron and which one gains electron. From our discussion from lesson 11, I hope you guys remember the trends. Remember, in trends, one of the clues that you have is, for example, is the metallic and the non-metal character of an atom. Non-metallic character usually tends to gain electron, while metallic character then tends to lose electron. And ions or ionic compounds, remember, are always a combination of a metal plus a non-metal. And from the trends that we learn from lesson 11, we know that metals tends to lose an electron while non-metals tends to gain an electron. So that's one clue that you can use to tell you that in here sodium is our metal, hence it loses an electron, while chlorine is a non-metal, which means it has to gain an electron. What other trends that we know that can support this idea is if we look at the IE or ionization energy. Remember that ionization energy is the energy that is needed in order to remove an electron. And the ionization energy has a trend that is going towards this way. Meaning, the more that you go towards the left and higher you go, the higher the ionization energy, meaning the more difficult it is to remove an electron. And if you look at the periodic table, Cl is found here while sodium is found on Cl is found on column 7 while sodium is found on column 1, which tells you that chlorine has a higher ionization energy than sodium, which means chlorine will less likely to lose an electron because it will require you more energy to lose an electron from chlorine than losing an electron from sodium. So from our understanding on the metallic and non-metallic character and ionization energy, even if you look at electron affinity and other trends in the periodic table, you would understand that sodium will be the one who will lose an electron, while chlorine will be the one to gain an electron, which tells you if we remove an electron from sodium, removing a negative charge, it will make our sodium positively charged, while our chlorine, when we add an electron to chlorine, it will make our chlorine more negatively charged. And that's how the start of the formation of ionic or the forming of an ionic compound starts. Also remember and understand that when we are removing electron, we want to remove the electron at the last configuration, or the last or the electrons found at the last configuration, which in this case we have to remove the electron here found at 3s1, which makes our sodium cation have an electronic configuration of 1s2, 2s2, 2p6. And we give that electron from 3s1 to our chlorine and add it on the electron found at 3p5, which gives our chlorine an ion electronic configuration of 1s2, 2s2, 2p6, 3s2, and 3p6. And if you notice now, since this is the electronic configuration of a positively charged sodium and negatively charged chlorine, you would see that they now follow the octet rule. They have 2s2 and 2p6, which is very similar to neon. It's like neon. And 3s2 and 3p6, which is very similar to argon. So it satisfies the octet rule. They may which means that if we combine these two, they are very satisfied being together. So question, but if this is now the electronic configuration of sodium, why is this sodium still sodium? Well, remember, we are only removing an electron. One of the what dictates whether an element is that element, for example, what dictates an element as sodium instead of being neon, even though they have the same electronic configuration, is not the number of electrons, which is what the electronic configuration is, but the number of protons. The number of protons in our positively charged sodium is still the same number of protons in this neutrally charged sodium. So we only remove electrons, we did not remove the protons. Hence, this is still a sodium, only missing one electron. Hence, the positively charged. So even though it has now the same electronic configuration as neon, it's only just the number of electrons. It's still the same atom because of the number of protons did not change. So I hope that is clear. So I hope you understand now what happens when we remove an electron and when we gain an electron in a ionic compound. So let's continue on. So why is this important? Well, now that they are satisfied with their octet rule, because of their positive and their negative charge, they're easily attracted to each other, because if you remember law from simple law in physics, opposite signs attract while opposite signs attract while same signs repel. So having a positively charged sodium and a negatively charged chlorine, they're bound to be attracted to each other, which will now lead us to our discussion in the formation of ionic bonding and ionic compounds. So an ion, which is a negatively charged ion, and a cation, which are negatively or positively charged ions, I hope you guys don't forget that, they're bonded together through what we call the electrostatic attraction. Electrostatic attraction is what we call the attraction between the negative and the positive charges. So this is, for example, a attraction between a sodium and fluorine. Fluorine is found also on the same group number as chlorine is, wherein we donate sodium, one of the electrons from sodium, we donate it to our electrons or to our fluorine, creating 8 electrons on the fluorine valence and 8 electrons on the valence of sodium. And we've proven this to be true from the electronic configuration, which now makes our sodium positively charged and our fluorine negatively charged. And because of this charge, they are now attracted to each other via the electrostatic attraction. So that's what creates the ionic compound. Ionic compounds are compounds formed by ions or the electrovalent bonding. Electrovalent bonding is basically the bonding between the positive and the negative charge, or it's basically the electrostatic attraction. So that's how ionic bonds are formed. And this, for this same reason, it's because of this electrostatic attraction, this attraction between the positive and negative charge. It's what gives our ionic compounds their very important characteristics, such as they become crystals. So our sodiums are example, or sodium chloride, our table salt, is an example of a crystal. It's because it's an ionic compound. Another thing is it gives our ionic compound a very high boiling point, a melting point, right? If you try to melt salt on a pan, if you put salt on a pan, it will require you a very high temperature before that salt melt. In fact, it will not even melt. It will just turn black and burn, but it will never melt. It's because because of this ionic compound that they have, this type of electrostatic bonding, or the electrovalent bonding that they have. Another thing though, that because of this electrostatic bonding, it gives our ion another property, which they become very good insulators when they are solid, meaning electric. When we talk about insulators, the travel of electrons, or basically electricity, they are not good. They are not good source for using. They're not good materials to be used if we want to travel electrons very fast. For example, wires. Wires are very good conductors because electricity travels really fast on wires. But because of this electrostatic bonding, which if you see, we have positive here, we have negative here, so when we combine them together, they basically become neutral. Electricity does not travel very quickly, or it does not travel on a solid ionic compound. But interestingly, ionic compounds are also very easy to dissolve. Again, it's because of the electrostatic bonding. If you take salt, for example, and drop it on water, it will easily dissolve, right? When we dissolve these materials, what happens is it breaks this bond. You would have positively charged sodium, and you would have negatively charged chlorine in your water. And because of those negative charge and those positive charge, what happens now is that our ionic compound in aqueous solution, it becomes a very good conductor. So it becomes a very good conductor of electricity. It's simply because of those negative charges that are now present, because we separate the compounds, or the elements, away from each other. So because of this electrostatic attraction, it's what gives our ionic compounds their very unique and very important property, which we exploit in a lot of chemistry, or in a lot of chemical applications all over our lives. So now let's talk about the different ions that we have. First, we have what we call the monoatomic ions. Monoatomic ions are basically ions that contain only one atom. So for example, our sodium, positively charged sodium, or our negatively charged fluorine are monoatomic ions as long as they're not yet combined. And they can either be positive or negative. Then we also have what we call the polyatomic ions, which are ions containing one or more atoms, but they can function as a single ion. Some of the examples is carbonate right here, which we have 3 atoms, CH and O, but overall they can function as if they are single ion. So if we use them on chemical reactions, they always function as a single ion. Another example is an ammonia, which is an NH4 with a positive charge. Even though we have two atoms, nitrogen, and 4 atoms of hydrogen, they are acting together as if they are one single ion. And then there's also, I hope you guys remember how to name our ions. When we name ions, for our cation, we just use the name of the element and add ion. So for example, sodium ion. And then for our cations, we usually have the name of elements and add an IDE ending. So for example, our fluorine is our cation, so our fluorine becomes fluoride. Our chlorine becomes chloride. So there's more ways on naming electrons. For example, in the transition metals, for transition metals, we have our common names, right? And we have a table for that on the module. So please look at your module and study some of the very common transition metal names on our ionic compound. And lastly, we have what we call the binary and ternary ionic compounds. Binary ionic compounds is basically a combination of two ionic compounds or two monoatomic ionic compounds, such as our sodium and our fluorine combined together. So our NaF here, or sodium fluoride, becomes a binary ionic compounds. Ternary ionic compounds is a combination of three or more ions, which happens usually with our polyatomic ions. So for example, if you have NH4 and combine it with another anion, then you would have three elements in there, or three atoms, which will make you have a ternary ionic compound. Now let's understand how to write the formulas for our ionic compounds. Also, for example, here you have your NaCl, which is a combination of sodium and chlorine, and then you have your sodium and hydroxide, which is a polyatomic ion. You have your OH right there, hydroxide, which is a type of polyatomic ion. Now let's talk about how do we write ionic formulas. Well, there's a very easy way to write the ionic formula. We're gonna stick with the very basic. So let's learn some of the strategy on how to write ionic formulas. First, we have to identify the component elements on our ionic formulas. Number two, determine their oxidation number. And three, we have to be able to balance the charges to create a neutral compound, which usually, if you notice, we're basically crisscrossing their oxidation number and make them the subscript. So let's look at these various examples. We have our periodic table to guide us in determining the oxidation number. So one trick here is, remember that if the element is found on your group 1, you usually have a +1 charge on any of these elements right here. So for example, you would have your lithium +1, sodium +1, potassium +1. As for our second column, you would have your +2, and then here you would have your +3, and then here you would have your -3, -2, and -1. So this is for column 1, column 2, column 3, and this is for column 5, column 6, and column 7. So these are one of the easiest ways to identify the oxidation number. Another thing that you have to identify is whether that element is a metal or non-metal. Because remember, our ions are a combination of non-metal and a metal. In order for you to identify whether your element is metal or non-metal, we use this staircase right here. Maybe let's use a different color. Let me use black. There you go. So by redoing this right here, this is your staircase. You use this staircase as your benchmark to identify whether your atom is metal or non-metal. Everything to the left of this staircase is metal. Everything to the right is basically non-metal. So that's how you identify whether the compound is metal and non-metal. Which this is important because it will tell you which one is your cation, which is usually your metal, and which one is your anion, which is usually your non-metal. So let's look at these following example. Lithium oxide. So what is the ionic formula for our ionic compound lithium oxide? Well, let's first look at our component elements. The component elements that we have is lithium, and oxide is the name of our anion, which tells you this is a non-metal. And from the way that we name an ion, we usually add an IDE ending from the name of our element, which means our oxide is actually oxygen. So after identifying the component elements, identify the oxidation number. Lithium is found on column A, which means lithium is actually positive 1. So lithium is positively charged. You do not need to write 1, but if you just write lithium with a positive charge, it means that's 1 charge of lithium. And then you would have oxygen. Oxygen is found on column number 6, and column number 6 has an oxidation number of -2. So our oxygen anion, or our oxide, is actually negative charge, and it is -2. So now, after identifying this oxidation number, what you have to do next is to balance the charge to create a neutral compound. What do we mean by that? Meaning, if we add our numbers, we should have a formal charge of 0. So 1, remember this is 1. So positive plus -2, what happens is you have a -1. So what it's telling you is we cannot just combine these two because we will not create a neutral compound. So what we need is we can add a few more numbers of these elements in order for us to balance the compound, which in this situation, what we need is we need to add one more lithium compound. So that's 1 positive, another 1 positive. It will give you 2 plus, right? Or positive 2 positive, and then you have your negative here, 2 positive plus 2 on 2 negatives, it will give you 0. So now this will tell you what your lithium oxide ionic formula is. So lithium oxide is actually going to be Li, lithium 2. This 2 right here is the number of lithiums that you have, and you would have your oxygen. Okay, because you only have 1 oxygen. So what is this crisscross? What is this crisscross method? Well, if you remove this is our original. What you would notice is this is basically these numbers right here, their subscript is the crisscross of their charges. So we have 1 lithium, so that will give you 1 right there. We do not need to write 1 because oxygen right there is considered as having a 1 there, so there's no need to write. So that is now the ionic formula for lithium oxide. So let's try, what about potassium sulfide? Potassium sulfide, potassium is found on, again, K is found as +1, so you have our K as +1. And sulfide is also found on here, same thing with oxygen, which is at column number 6. So that's our oxygen -2. So it means here we need 1 more potassium, so which will give us K2, because we have 2 potassium and 1 oxygen. So we would have a K2O as our potassium sulfide, which, in going back to crisscross method, which just tells you that you can just place the number there. So why am I teaching you this method of adding more elements? Is because for you to understand why do we do crisscross. Crisscross is the shortcut, but the principle is we have to have neutral compound, and in order for us to have neutral compound, it means we need to add 1 more potassium. So potassium sulfide is basically K2O. Next, we have ferric oxide. Ferric oxide is a transition metal. If you look at your table on your module, you would know that ferric from IC, it means you need to choose the higher oxidation number, and the higher oxidation number for iron is +3. And then you would have another, again, oxide, which is -2. So in this situation, if you look here, so how am I going to balance this, right? Well, you basically have to kind of like add them. So we have +3 and -2. So if we add them, it means we have +1. It is not it's not a neutral compound yet because we have +1. It means we need one more negative. So let's try and add another. Maybe let's write it here. This is +1. So what if I add another oxygen? So what happens is now we have +3 and we have -4. So +3 plus -4, we will have now -1. So we're missing one more negative. Right? So it means we need one more positive. So let's add another ferric, or another iron +3. So what we ended up having now is +6 plus -4, which gives us -2, which means we need two more, or +2, which means we need -2 in order to balance this. So let's try to add another negative oxide, and what you can see now is we have a neutral compound because we have +3 plus +3 is +6. You have -2, -2, and -2 is -6, which gives us 0, which means the compound for ferric oxide is Fe2O3. So that is the formula for ferric oxide. And if you notice, if we go back to our original elements, it's basically again just crisscross method, right? So that's how we write the ionic formulas for our ionic compounds. Aluminum oxide, aluminum is found at +3. Oxide is -2. So using the crisscross method, you would know that you would have Al2O3, right? So that is how you would write the ionic formulas. As you can see, we've been using mono ions or monoatomic ions so far. What if we have polyatomic ions? Nitrate here, please do not confuse with the nitride. Nitride is N, but nitrate and nitrite are polyatomic ions. So how, you may be asking, how can I know if this ion is polyatomic? Well, sadly, in order for you to know whether they are polyatomic ions is for you to memorize and be familiar with what the polyatomic ions are. So in order for us to answer this, we need to have an idea of the common polyatomic ions, which in our situation here, we have a nitrite. So this right here, which means our compound is NO3 with 1 negative. So our calcium is found on, where's our calcium? Right there. Our calcium is right there. So calcium is +2 and nitrate is NO3 negative. So as you can see here, we have, if we add these two together, we would have +1, which means we need one more negative. So we will add NO3 1. So we have -2 plus 2. We will now have a neutral compound because we will have 0 formal charge. So how are we going to write this? or we write this by basically writing Ca, and then we need to have a parenthesis for our NO3 because we have our 3 there, and add our 2, which tells us we have 2 NO3, which means we have 2 polyatomic ions. And again, if you use the cross method, it's just telling you that you would have 1 Ca and 2 NO3. Okay, so that's how you write the ionic formula for polyatomic ions. It's basically the same thing even when you have monoatomic ions. It's the same principle. So about writing names, we have Al2 and SO4. Well, for our polyatomic ions, remember in naming ionic formulas, for our cation, in this situation, our cation is aluminum. For cation, we just write their names. And then for our polyatomic ions, we just have to write the name of our polyatomic ions, which in this situation, we have SO4 or sulfate. Right? So we have aluminum sulfate. So that's how we write the ionic formulas and a little bit of naming. So I hope that is clear. If you guys have any questions, please do not hesitate to contact me and ask me and message me. Okay. Now, so after identifying how to write ionic formulas, let's write ionic structure. How do you write ionic structure? Well, we employ what we call the Lewis selection dot symbol, or the Lewis selection dot structure, or in most easy way, just Lewis structure. Remember, Lewis structure is what we use to identify the valence shell. We've used this before. Elements that are found in group 1 has 1 atoms in their valence shell. The same thing for those found in group number 2, and so on and so forth. Using that idea, then we basically write dots and write the Lewis structure for our compound. So let's try some of these examples. So we have our Na and our Cl. Na is found on group number or group A. So it means we have our Na with 1 electron. And then our Cl is basically found on group number 7. So which means our Cl will have 7 electrons, right? So what happens in the Lewis structure for ionic compounds, and we know this is ionic compound because this is a combination of a metal and non-metal. So it happens, since our sodium is our metal, it is ready to lose an electron. So it will donate one of its electron to sodium, which will now give our Na, we'll write it in bracket, a positive charge, and our Cl another bracket, but this time it will have 8 electrons around it, and it will have negative. So this is now the Lewis dot structure for our sodium chloride. Now let's look at our magnesium fluoride. Magnesium is found at column number 2, so which means our magnesium will have 1, 2, and our fluorine is found on group number 7. So we have our fluorine 1, 2, 3, 4, 5, 6, 7, and since we have 2 fluorine, you will write 2 fluorine, 1, 2, 3, 4, 5, 6, and 7. So what happens is these electrons, since this is our cation, our metal, and fluorine is our non-metal, our fluorine tends to gain more electron than magnesium. So magnesium will donate one of its electrons to our fluorine, and it will donate its another electron to fluorine, which will tell us that we will have a magnesium with 2 positive, and beside it, it will have fluorine 7, 8 negative, and you can write the other fluorine here, 1, 2, 3, 4, 5, 6, 7, 8 negative. Or you can also write it this way, Mg 2 plus and 2, 1, 2, 3, 4, 5, 6, 7, 8 negative. So you can either write it this way or this way. How about K2? Oh, K has 1 electron on its valence shell, and we have 2 of them. And then we have oxygen that is found on column number 6, which means we have 1, 2, 3, 4, 5, and 6. And our potassium is our metal, so it donates electron. Which gives us K plus, and will have an oxygen 1, 2, 3, 4, 5, 6, 7, 8, 2 minus, and another K plus. Or again, you can write it this way, 2 K plus and two minus. So that's how the Lewis dot structure is. So it's telling you where the electrons are, and the electrons are found on the oxygen. And lastly, aluminum 2O3. Aluminum is found on number 3, so we will have aluminum 1, 2, 3, aluminum 1, 2, 3, and we will have 3 oxygen 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, and 6. So what happens is these 2 electrons are donated in this electron, and these 2 electrons are donated in this oxygen, and these 2 electrons are donated in this oxygen, which will tell you that you will then have a 2 Al 3 plus, and let's rewrite that. You will have your 2 Al, this is 3 plus because it lost 3 electrons, and you will have 3 O2, 3, 4, 5, 6, negative 2. So that is the Lewis dot structure, or how would you write the ionic structure for our ionic compounds. So I hope it's quite easy. It's really not that difficult. You just need to be able to understand where the electrons are being transferred, or where they are being given. So I hope everything is clear. Thank you so much, guys. If you guys have any question, please do not hesitate to message me. May you guys have a great day, and thank you so much.